All right, this will be an introduction to solving exponential equations. So we're going to get more in depth with exponential equations later on in the unit, kind of before the holiday break and possibly after the new year as well. But these are relatively basic exponential equations. Every one of the equations you see, the primary goal is going to be able to write these equations as a single base to an exponent, to a power, on one side, and then using the same base on the other side. So I'm starting with two relatively simple examples, and then the other two examples will be a little bit more complicated. So we could take a look at this example A here, and hopefully we can notice that this 32 can be rewritten as a power of 2, right? Because we've got 2 to the 2x minus 7. So we can rewrite 32 as 2 to the 5th power and really just substitute 2 to the 5th for 32. So we have 2 to the 2x minus 7 equals 2 to the 5th. And now these two exponents must be equal, right? If you just think about that, 2 to some power equals 2 to some other power. Those two powers have to be equal. There's no way for them not to be. So we can simply set the exponents equal to each other and then solve the equation that remains. X equals 6. And then we can double check and plug this 6 back in here. 2 times 6 is 12, minus 7 is 5. That's 2 to the 5th, and 2 to the 5th is indeed 32. So this 6 does work. Okay, so just to review, those steps were first, we're trying to write this first, we want to find a common base on both sides. Of the equation. And then in this case, it wasn't necessary to use exponent rules to simplify. In the next case, it will be. So we're going to use exponent rules to simplify if necessary. We'll see that in the next example. And then we're going to set the exponents equal and solve. Okay, so let's take a look at this next example. This one's a little bit trickier. It's a little harder to see. Okay, we need to take a look at this 1/27th and this 9 and think about what base we can write 1/27th and 9 as. Hopefully, you see that we can write it with a base of 3. The 9's a little easier, so we'll start over here. 9 is 3 squared, so I'm going to replace the 9 with a 3 squared, and I'm still going to raise that 3 squared to the 3x plus 4 power. Now 1/27th you might recognize is the same as 1 over 3 to the 3rd, right? That's the same as 1/27th. Well, 1 over 3 to the 3rd can be rewritten as 3 to the negative 3rd power. Okay, maybe you saw that 1/27th was 3 to the negative 3rd power, and that's fine too. But if you need this intermediate step, that's okay. So we have 3 to the negative 3rd to the x minus 1. And now, we have 3 to a power to another power, and we have 3 to a power to another power. And this is a situation where we're going to need to use our exponent rules to simplify this exponent here, right? And this is a power to a power property, and that tells us that we need to multiply. So we're going to have 3 to the negative 3x plus 3. Right? I just distributed that negative 3x. And then we're going to have 3 to the 6x plus 8. And at this point, we have the same base raised to different powers. We can conclude that these two powers must be the same, and we can go ahead and solve that equation. Negative 3x plus 3 equals 6x plus 8. So we have negative 9x is equal to 5, which makes x equal to negative 5 ninths. And again, we could go substitute that in and just verify that it works. And you'll see that it does. All right, these two examples are a little bit trickier. Still the same exact idea, same exact process as we applied before, but they're just a little bit more complicated. Okay, this E here, E is a base. It's called the natural base. We're going to learn more about E in class in a couple of days, but for right now, it's just a base. It's just some number. We don't need to really worry about what number it is, but it's just a base. Okay, so if we think about those steps from before, we're trying to get everything into a common base. It looks like E is going to be our base. Can't really do anything with the left side right now, so I'm going to leave that alone. E to the negative x squared. Over here I can do some simplifying, right? This is e to the x to the 2. So this is going to be, we're going to multiply x and 2. So we're going to have e to the 2x. And then if I multiply that by 1 over e cubed, think of this as like e to the 2x over 1 times 1 over e cubed, I end up with e to the 2x over e cubed. Okay, and so now we have a quotient here, a quotient of the same base, and hopefully you remember that we're going to subtract the exponents here. Right, I'll write that down here. So we can subtract the exponents when we divide by the same base. So we end up with e to the negative x squared equals e to the 2x minus 3. All right, so now we have the same bases on both sides. We could set our exponents equal to each other. This is a little different because now I'm dealing with a quadratic, an x squared. So negative x squared equals 2x minus 3. I'm going to bring the negative x squared to the right side of the equation just so that I can make it deal with a positive x squared instead of a negative x squared. A factor. Oops, x minus 1. And x can either be negative 3 or 1. And if I go back up here and double check that, right, this is the opposite of x squared. So if I plug negative 3 in here, this becomes e to the negative 9th. And then negative 3 to the 2, negative 3 to the 2 is negative 6, minus 3, or over 3 over e to the 3rd. So that negative 6 minus 3 is going to become e to the negative 9th as well. And I can do the same thing with 1 and still verify that that works. It's pretty rare that you get an extraneous solution with these types of exponential equations. The ones we do later on, we will see extraneous solutions on a relatively regular basis. So it's a good habit to just get in to double check your solutions. All right, so the final example we have here, it's a bit of a doozy. There's a lot going on. Hopefully you recognize that the common base we're going to be able to convert all of these to is 5, because I could rewrite 25 with a 5. I could rewrite 1/5 certainly with a 5, and I could also rewrite 125 with a 5. But this is interesting. Here we have this square root that we've introduced. And not only do we have a square root, but we've got a square root of 125, which is not a perfect square, and we're raising that to a power, a negative power at that. So there's a couple of different ways to approach it. So the way I'll approach it is one of the ways. It's not the only way. And if you have another way, feel free to run it by me. But I'm going to start by rewriting everything into powers of 5. Right, so this 25 is going to become 5 squared. 5 squared to the x plus 2. The 1/5 is going to become 5 to the negative 1. If you're not comfortable with your negative powers, you're going to want to get comfortable. Right? 1/5 is 5 to the negative 1. And we have that to the 2 minus 3x. And then 125 is 5 to the 3rd power. But remember that this square root is actually to the 1/2 power. So hopefully you remember that. So I'm going to just kind of go off to the side a little bit up here and just remind you that the square root of 125 is the same as saying 125 to the 1/2 power, right? So this is really 5 to the 3rd to the 1/2 power. Okay, and then we're going to raise all of that to the negative 2x. So I'll write that out here. 5 to the 3rd to the 1/2 power. That's your square root of 125, right? So this portion of it is right here. And then I'm going to raise all of that to the negative 2x power. All right, so now I've got a bunch of simplifying to do. So 5 squared to the x plus 2, I could simplify to 5 to the 2x plus 4. Right, power to a power, I multiply. I'm going to do the same thing here. 5 to the negative 1 to the 2 minus 3x. That I'm going to multiply the negative 1 by 2 minus 3x, so I get negative 2 plus 3x. And then over here, I get 5. I'm just going to write this in 2 steps. 5 to the 3/2 to the negative 2x. I'm going to write that in 2 steps for now, just so that we can see it. Okay, now here, this is a base times a base raised to 2 different powers. So I'm going to add those powers. That's what the rule says. 2x plus 4 minus 2 plus 3x. And this is your power to a power rule. So 3/2, oh sorry, I should have written it like this. 5 to this whole thing, this is the whole power here, equals 5 to the 3/2 times negative 2x is negative 3x. Right? 3/2 times negative 2x is negative 3x. So now I have my single base on both sides, the same base on both sides. I have my power on both sides. I can set my powers equal to each other. 2x plus 4 minus 2 plus 3x equals negative 3x. This looks like 5x plus 2 equals negative 3x. So 2 equals negative 8x, which gives me x equals negative 1/4. So again, this one is the most complicated type of example that you'll see. There's a lot going on. There's negative powers, there's a square root. We have to remember the square root is a 1/2 power. Okay, so this is pretty complicated. All the others are pretty standard type of examples. Example D, I would say, is kind of is an above and beyond for this particular class, but it's certainly worth taking a look at and giving it a try.